Hello everyone. This session is about single-phase full converter for DC separately excited motor. We know that single-phase full converter is a two-quadrant converter. When we feed the separately excited DC motor with the help of the single-phase full quadrant converter, then we can able to get the forward motoring mode and the reverse braking mode. For this, we need to feed the armature of the DC motor with the help of the full converter. The field winding should be connected to a constant DC source. With the help of this arrangement, we can able to get the variable speed of operation by changing the output voltage of the converter. And we all know that there are two modes of operation of the single-phase full converter. This is the single-phase full converter circuit, which consists of four thyristors T1, T2, T3, and T4, which is fed from a single-phase AC voltage. This is the armature circuit of the DC motor. We can operate the converter in continuous or discontinuous conduction mode of operation. And both the modes can be operated either in the rectification mode or in the inversion. For operating the converter in the rectification mode, the firing angle should be less than 90 degrees. And for an inversion mode, it should be greater than 90 degrees. Let us see the operation in the continuous conduction. In continuous conduction mode, the load current, that is the armature current, is always greater than 0. And we have to trigger the devices T1 and T2. We have to take alpha less than 90 degree, and let us consider that T1 and T2 are triggered at the firing angle alpha. And during the positive half cycle, T1 and T2 are triggered at firing angle alpha. When T1 and T2 are triggered at firing angle alpha, then current will flow through T1, through the armature circuit, through T2 and back to the source. So during that time, the armature voltage will be equal to Vm sin omega t. During the negative half cycle, when T3 and T4 are triggered at pi plus alpha, the armature is connected to Vs through T3 and T4. The waveforms for the rectification mode and the inversion mode are given in this diagram. This figure shows the waveform for rectification mode, which is also called as forward motoring mode. When T1 and T2 are triggered at alpha, up to pi plus alpha, when T3 and T4 are triggered, the output voltage will follow the input voltage waveform. When T3 and T4 are triggered at pi plus alpha, until T1 and T2 are triggered at 2 pi plus alpha, the output voltage will be the mirror image of the input voltage waveform. The armature current is always positive and it is always greater than 0 because we have considered the continuous conduction mode of operation. And these are the waveform for the inversion mode of operation. It is also called as reverse braking mode, in which the alpha is taken as greater than 90 degrees. Here, again, when T1 and T2 are triggered from alpha to pi plus alpha, the output voltage will be same as that of the input voltage. When T3 and T4 are triggered, or when T3 and T4 are conducting, the output voltage will be the mirror image of the input voltage. Again, here, the armature current waveform is shown here, which is always greater than 0, since we have considered the continuous conduction mode of operation. Now, we can derive the average output voltage for the converter. So, to derive the average output voltage, we have to take the output voltage waveform. The average output voltage is, or the output voltage at the armature circuit is given by Va equal to 2 by 2 pi integration from alpha to pi plus alpha Va d omega t, where Va is nothing but Vm sin omega t. So after integration, we will get minus cos omega t, and after substituting the limits, we will get the average output voltage of the converter, which is feeding the armature circuit of the separately excited DC motor is 2 Vm by pi into cos alpha. We can obtain the speed torque equation of the DC separately excited motor, which is given by omega m is equal to Va by k minus T Ra by k square. Substituting for Va as 2 Vm by pi into cos alpha, we will get the speed equation in terms of torque, and the alpha as given by omega m is equal to 2 Vm cos alpha by pi k minus T Ra by k square. This is the speed equation which relates the speed and torque of the DC separately excited motor fed by single phase full converter. Now let us see the discontinuous conduction mode of operation. In this mode, the armature current is not continuous. It reaches zero before the next pair of devices are turned on. At omega t when T1 and omega t equal to alpha when T1 and T2 are triggered, the armature current starts from the zero value and flows through T1 and T2 to the armature winding. The armature voltage Va follows the input voltage. At omega t equal to beta, before pi plus alpha, when the next pair of devices are triggered, the current reaches zero. So from beta to pi plus alpha, the armature current is zero because no device is in the on condition during that period. Hence, the armature voltage during that period from beta to pi plus alpha will be equal to the back EMF of the armature circuit. Here again, we will be having the modes for rectification and inversion. During the discontinuous conduction mode, the drive operates in the two intervals. One is the duty interval where the armature current is greater than zero, which happens from alpha to beta, and during that time the motor is connected to the supply voltage Vs through the devices conducting. And the second interval is the zero current interval, which happens between beta to pi plus alpha. The motor is disconnected from the supply, and during that period the armature current is zero, and during that time the armature voltage is equal to back EMF E. Now let us see the waveforms for the rectification mode of operation. This is the waveform for rectification mode during the discontinuous conduction mode, which is drawn for alpha less than 90 degrees. Here we can see that at this point alpha, which is less than 90 degrees, we are triggering T1 and T2. So T1 and T2 will be conducting from alpha to beta. At beta, the armature current becomes zero. So from alpha to beta, T1 and T2 are conducting. During that time, the armature voltage is same as the input voltage Vs. And at beta, when the armature current becomes zero, from beta to pi plus alpha, since no device is in the on condition, the armature voltage will be equal to the back EMF E. And again at pi plus alpha, when we trigger T3 and T4, the armature current will rise from zero and it reaches zero again at pi plus beta. From pi plus alpha to pi plus beta, the armature voltage will be the mirror image of the input voltage. From pi plus beta to the next instant of triggering, which is 2 pi plus alpha, the armature voltage will be equal to back EMF of E, as during that time no device is in the on condition. This is the waveform for forward motoring mode during the discontinuous conduction mode. Now let us see the waveform for the inversion mode or the reverse braking mode of operation, where we have to take alpha greater than 90 degrees. So when we trigger T1 and T2 at alpha greater than 90 degree, up to which the armature current starts from zero and it again reaches zero at beta. So during the time from alpha to beta, when T1 and T2 are in the on condition, the output voltage waveform is the same as that of the input voltage waveform. At beta, when T1 and T2 are turned off, the back EMF during this mode, in the reverse bracket mode, we have to reverse the back EMF, the polarity of the back EMF. During that time, the output voltage will be equal to the back EMF, which is minus E, which exists between the armature terminals. Then at pi plus alpha, we will be triggering T3 and T4. And again, during that time, the armature current again will rise from 0 and it will reach 0 again at pi plus beta. During that time, the output voltage waveform follows the mirror image of the input voltage waveform. So these are the waveforms for the reverse bracket mode during the discontinuous conduction mode of operation. Now let us derive the peak torque equation for discontinuous conduction mode, for which we need to find the average output voltage of the converter. So average output voltage for discontinuous conduction mode is obtained with the help of this equation. So VA is equal to 2 by 2 pi. From alpha to beta, the output voltage follows the input voltage waveform. From beta to pi plus alpha, the output voltage is equal to the back EMF. So substituting this and after integration and after substituting the limits, we will be getting the average output voltage as VA equal to 1 by pi Vm cos alpha minus cos beta plus E into pi plus alpha minus beta. Now we need to substitute this equation in the speed torque equation, wherein VA is equal to this value. After substituting this, we will be getting the speed equation as omega m equal to 1 by k pi Vm cos alpha minus cos beta plus E into pi plus alpha minus beta minus TRA by k square. We know that the back EMF is a function of speed omega m. So we can write back EMF is equal to k into omega m. So substituting for E is equal to k into omega m in the above equation and rearranging the terms, we will get omega m equal to 1 by k pi Vm cos alpha minus cos beta plus k omega m into pi plus alpha minus beta minus TRA by k square. After rearranging everything and taking omega m to the left hand side and after simplifying all the above equation, we will get the equation for omega m as 1 by k into beta minus alpha into Vm cos alpha minus cos beta minus pi TRA by k square into beta minus alpha. This is the speed torque equation of DC separately excited motor fed by single phase full converter in the discontinuous conduction mode. Now we will derive the critical speed equation for this drive. Critical speed is that speed above which the discontinuous conduction mode occurs. We have seen that the drive can operate either in the continuous conduction mode or in the discontinuous conduction mode. During the discontinuous conduction mode, the speed of the motor will be greater than this critical speed. So it is that speed which decides whether the drive is operating in the continuous mode or in the discontinuous mode. In order to derive this one, we have to consider the armature current equation and we need to derive the expression for critical speed. Now let us consider the armature current during the duty interval. So during the duty interval, if we write the KVL equation of the armature circuit, we can write the KVL equation as Vs is equal to IaRa plus La into the Ia by dt plus E. This is a first order differential equation which can be solved with the help of taking the Laplace transform and then taking the inverse Laplace transform. The solution of this equation will be Ia of omega t equal to Vm by Z sine omega t minus phi minus E by Ra plus K1 into e power minus t by tau A. So this equation consists of two parts. One is the steady state current part, uh, which consists of the sinusoidal component and the constant component, and another one is the exponential component. Here, Z is the impedance of the armature circuit, which is given by square root of Ra square plus omega La square. And we can write tan phi as omega La by Ra or tan phi as omega tau A, where tau A is nothing but La by Ra, which is the time constant of the armature circuit. And we can also write cot phi as 1 by omega tau A. Now this is the current waveform. In order to find the K1 value, we need to substitute the boundary condition. Let us take the boundary condition at alpha. At alpha omega t equal to alpha, we get Ia equal to 0. So substituting Ia value at that point of alpha, we will be getting 0 equal to Vm by Z sine alpha minus phi minus E by Ra plus K1 e power minus alpha by omega tau A. And this will give K1 value as E by Ra minus Vm by Z sine alpha minus phi into E power alpha by omega tau A. Substituting this value of K1 in the Ia equation, we will get this expression. And substituting for cot phi and rearranging, we will get the Ia of omega t expression as this one. This is the equation for omega t between alpha and beta. Again, we have to take the next boundary condition, that is at omega t equal to beta. Again, at that point, Ia is equal to 0. And so substituting that boundary condition, we can equate this equation to 0. And by solving the above equation, we need, in order to find the critical speed of operation, we need to solve this equation by some iterative method, and we need to substitute beta equal to pi plus alpha because the boundary between the continuous and the discontinuous conduction is decided by beta value. If at beta equal to, if we make beta equal to pi plus alpha, we can just avoid the discontinuous conduction mode because this is the boundary between the continuous and the discontinuous conduction mode. So if we substitute that case, if we substitute beta equal to pi plus alpha, and if we substitute omega value as the critical speed in this equation, in this first equation, we will be able to get the expression for the critical speed, which is omega mc. So substituting the bound conditions beta equal to pi plus alpha and d is equal to k into omega mc in the equation 1 and rearranging the terms and simplifying it. So after rearranging and simplification, we will be getting the critical speed expression as omega mc is equal to Vm Ra by Zk sine alpha minus phi 1 plus e power minus pi cot phi divided by e power minus pi cot phi minus 1. So this is the expression for critical speed of DC separately excited motor fed by single phase full converter. Now, in order to draw the speed characteristics, we need to find the no-load speed. So no-load speed is that speed which occurs when Ia equal to 0. And Ia equal to 0 is possible only when the devices are not conducting. And this can happen only when the back EMF is greater than or equal to Vm for alpha less than 90 degrees. And for alpha greater than 90 degree, it will happen only if E is greater than or equal to Vm sine omega t. So substituting these two conditions, we can have E equal to Vm for alpha less than 90 degree. We will be getting the no-load speed as omega m naught equal to Vm by k. And for alpha greater than 90 degree, we can get the no-load speed as Vm naught equal to Vm sine alpha by k. So after obtaining the no-load speeds, we can draw the speed torque characteristics for varying values of alpha. So this curve shows the speed torque characteristics of separately excited motor fed by single phase full converter for both forward and motoring mode. Here we can see that for alpha less than 90 degree, the no load speed is Vm by K. For alpha greater than 90 degree, the no load speed starts from the point Vm by K into sin alpha. So this is the boundary line which divides the characteristics from continuous to discontinuous conduction mode. When the speed is greater than omega mc, the discontinuous conduction mode of operation will take place, and for speeds less than critical speed, the continuous conduction mode of operation will take place. So this is the overall speed characteristic of the DC separately excited motor fed from single phase full converter. Thank you.